All right, today we're going to decode a secret language, one that's happening all around you every single second of the day. It's the language of flow, and it describes everything from the air you're breathing right now to the waves in the ocean. So yeah, let's dive right in.
So, have you ever just stood by a river and noticed this? It's something we've all seen. The water just seems to zip along in the middle, but near the edges, it's moving super slowly. It feels kind of obvious, but that simple observation, that's a huge clue that there are these powerful, invisible rules at play dictating exactly how that water moves.
And that's our whole goal here today. We're not just going to talk about fluid motion. We're going to give you the actual tools to see it, to visualize the patterns that engineers and scientists see every day. Seriously, by the end of this, you will look at that same river in a completely different way.
Okay, so first things first, if something like air or clean water is basically invisible, how in the world do you track its movement? It seems impossible, right? Well, we have to find a way to make it visible, and we do that using three really key concepts.
The first one is called a pathline. And honestly, this is the most straightforward idea of the three. Just imagine you could follow one single speck of dust in the water and track its entire journey over, say, a minute. The line it traces out, that's its pathline. Think of it like the personal travel diary of that one little particle.
Next up, we have the streak line. Now, instead of following just one particle, imagine you keep a probe fixed in one spot and continuously release a stream of dye. The line that's formed by all those different dye particles at one single moment in time, like in a photograph, is the streak line. And the absolute best way to picture this is the smoke rising from a candle. That beautiful wafting plume, that's a perfect real-world streak line.
And finally, we get to the streamline. Now, this one's a little more abstract. It's more of a mathematical tool. It's an imaginary line that we draw through the fluid that, at any point, shows you the exact direction the fluid is moving at that very instant. But here is the absolute key takeaway, the part that makes this so useful. When the flow is steady, and that just means nothing's changing over time, the path line, the streak line, and the streamline all become the exact same line. It's an incredibly powerful simplification that engineers rely on constantly.
Okay, so now that we have some ways to visualize flow, how do we actually describe it? How do we classify it? Well, it turns out you can describe almost any kind of fluid motion by asking just four simple questions. Think of this as your go-to diagnostic kit for flow.
The very first question is all about time. If you could just stare at one single point in the fluid, is the velocity there always the same? If the answer is yes, then the flow is steady. It's predictable, it's constant. But if that velocity is fluctuating, speeding up, slowing down, then the flow is unsteady. Question 2 is all about space. So if you could freeze time for just one instant, is the velocity the same everywhere you look? In a long, straight pipe where nothing's changing, yeah, it's pretty much the same. We call that uniform flow. But what happens if that pipe suddenly gets narrower? The fluid has no choice but to speed up. Now the velocity is changing from point to point, and that makes it non-uniform flow. Question 3 really gets to the personality of the flow. Is it orderly or is it just complete chaos? Laminar flow is the orderly one. It's smooth, it's elegant. The fluid particles move in these neat parallel layers. Turbulent flow is the exact opposite. It's a chaotic, messy jumble of eddies and swirls with particles just zigzagging all over the place. And all that chaos, it creates a ton of energy loss, which is why it takes so much more power to pump water at high speeds. So how do we know when a flow is going to switch from that nice, smooth state to total chaos? Well, for that, we use a special little tool called the Reynolds number. It's a value that cleverly combines the fluid's speed, its density, and its viscosity, which is really just a fancy word for how thick it is. For flow inside a pipe, there's a kind of tipping point. Once that number gets above roughly 4,000, you can bet that flow is going to be turbulent. It's an incredibly powerful number for designing everything from pipelines to airplanes. And our final question is a little more subtle. It's about whether the individual fluid particles are actually spinning as they move along. If they just kind of cruise along without rotating, we call the flow irrotational. But if they're tumbling end over end, like a log rolling down a hill, then the flow is rotational. And you usually see this spinning happen right near the boundaries of an object, thanks to friction. Now you might be thinking, wow, all these classifications can get pretty complicated. And you'd be right. That's why scientists often start with a simplified model to make the analysis easier. But it's really, really important to understand how that perfect model differs from the messy real world. Let's take a look.
So, on one hand, you have the ideal fluid. This is a total fantasy concept. It has zero viscosity, meaning no friction at all, and it's incompressible, so you can't squish it. It doesn't really exist, but boy, does it make the math easier. On the other hand, you have real fluids, water, air, everything that actually exists. They all have some internal friction, and they can all be compressed a little bit. So, why does this difference even matter? Well, it all comes down to something called the boundary layer. Now get this. In a real fluid, the very thin layer of fluid that is physically touching a surface is completely stuck to it. Its velocity is zero. Then, as you move away from the surface, the velocity quickly ramps up. That tiny region where the velocity is changing is the boundary layer, and it's where all the important messy effects of viscosity happen. What's amazing is that outside of that tiny layer, the fluid often starts behaving just like our simple ideal model.
Okay, with all these different concepts in our back pocket, there is one single unbreakable law that ties everything together. It is the most important principle in all of fluid dynamics.
And it's the principle of conservation of mass. You can't create fluid out of thin air, and you can't make it just disappear. I know, it sounds almost too obvious, right? But the implications of this simple idea are absolutely profound. This simple truth leads us straight to the law of continuity. Just picture water flowing through a pipe. Whatever volume of water goes in one end has to come out the other. Now, what if the pipe gets narrower? You're forcing that same volume of water through a much smaller area. The only way for that to happen is for the water to speed up. It is a direct trade-off between area and velocity, and it governs everything from why your garden hose speeds up when you cover the end to how an airplane wing generates lift.
So we have covered a lot of ground here. How to visualize flow, the 4 questions that help us describe it, and the golden rule that governs the whole thing. You now have a totally new lens for looking at the world.
Is that smoke laminar or turbulent? Is the wind whipping around that building steady or unsteady? You actually have the vocabulary now and the concepts to start answering those questions. You can speak the language of flow.
So the next time you see a river, or even just watch leaves blowing in the wind, I want you to take a second. What are you going to see? Is it just going to be water and air? Or are you going to see the invisible dance of physics playing out right there in front of you?